Hi, very good days. Uh, right now, I will present one of my project with the entitle of simulation of liquid ammonia spray characteristics for gasoline direct injection under engine relevant condition. This is my presentation outline, which is that I will start with introduction, and then I will go for objective, scope, the methodology for my project, and then I will discuss the result that I found during this project, and then I will conclude all the finding for this project. So as an introduction, we can say that a standard passenger vehicle emit mostly 4.6 metric ton of carbon dioxide annually, and then sustainability alternative fuel actually can help to reduce emission and make transportation more environmental friendly. One of a promising option is gasoline direct injection (GDI) technology, which improve fuel efficiency and control. And one more other interesting is ammonia. We found that a highly promising clean fuel alternative, as they do not produce carbon dioxide emission when burned and have other desirable properties. So with this advanced line to minimize the negative effect of combustion on climate change and ensure a sustainable transportation future, I will go for the study of characteristic for gas reduction engine with the liquid ammonia that we will spray directly into the combustion chamber. So from there, my objective of this project is first to model the injector tip and chamber geometry, then simulate the spray injection fuel process using computational fluid dynamics, and then from the simulation, we want to determine ammonia nozzle flow and spray characteristic at various conditions, focusing on mixture formation. And during this project, the simulation will use the CFD analysis for combustion process, and then the nozzle parameter are constant. We set constant for the nozzle parameter, and the main variable that we play during the simulation is fuel inlet pressure, which is that we setting for 100 bar, and then chamber pressure, which is that the 10 bar. So the main data that we want to abstract from the simulation is the spray pattern and atomization process in spark ignition injector. So for the methodology, that's the flowchart. I think I don't need to explain more on this flowchart. And then this is the model for our project, which is that we have the injector and combustion chamber, and then the right side we have the meshing of the injector, and then the below one is the detail meshing, which is the critical part at the nozzle injector of the combustion chamber. Then for the meshing properties, we use tetrahedral meshing with the element size of 0.9. We have a number of knot around 5 million knot with the skewness 0.88. And then this is the boundary condition that we're setting for this simulation. At the inlet, we initialize with the fuel at 298K with 190 bar, which reaches the inlet boundary condition with 219. Okay, that's the similar one. And then for the chamber, we initialize with the ammonia at 298 Kelvin with 3.15 bar with the open boundary at the chamber outlet. And the pressure outlet, we use the atmospheric pressure for the outlet. For the parameter setting, for this simulation, we use the ANSYS Fluent for the study and a density base solver coupled with a modified pressure implicit with PISO, which is the splitting of pressure implicit with splitting of apparatus. to solve the compressible flow equation. And we use the second order central difference method for temporal discretization, while second order upwind skin for spatial discretization. The RNG-KS flow model used to predict the turbulent flow characteristic for the turbulent model, and the physical properties of the injected fluid influence the flow and the cavitation characteristic in the injector nozzle, which is reflected in the mass flow rate, effective nozzle diameter, and the velocity at the nozzle exit. For the spray simulation, the effect of nozzle, the effect of in-nozzle flow on near spray behavior actually can be determined by nozzle discharge coefficient, injection flow rate profile, and initial droplet size distribution, which are widely employed in similar spray studies and show reasonable result compared with other researchers. In addition, a variable time step methodology based on the Coren-Friedrich-Levy number is adopted to accelerate the computation while maintaining the good accuracy of the result. And then for the result, firstly, I want to show the result of diameter and length of velocity penetration of GDI spray. So one of the essential characteristics that interesting in the study is the diameter and length of the velocity penetration GDI spray. Basically, the spray penetration is a distance the fuel spray exit in the injector nozzle before it spread out or widen. The value for each injector pressure on the diameter and length of the velocity penetration will plot into graph as shown in the slide at the fuel injector location in the chamber. So from there, we can see that the spray distance or length from the injector nozzle before it begins to disperse is influenced by injection pressure. The spray often travels further before it spread or disperse when injection pressure is increased because greater velocities penetrate at higher injection pressure. However, we can see that penetration is also influenced by the length of the injection. As the gasoline is injected and propelled forward for longer time, a longer injection duration enable to larger spray penetration distance. As a result, you can see that compared to injection pressure of 50 bar, length velocity penetration tend to rise at 80 bar and 110 bar injection pressure. The increasing injection pressure typically result in a narrower spray width. Higher pressure improve the atomization process, producing smaller, more concentrated droplet in the core of the spray cone. So the next is the effect of spray injected into the atmosphere at a different injection pressure and duration. This one, the figure shows the velocity penetration into the atmosphere pressure at different injection duration with the pressure of 50 bar. So the result for the influence of atmospheric pressure on the spray penetration at various injection pressure and duration as shown in the figure. And from the figure, we can see that the simulation showed that the shorter injection length may produce larger droplet, whereas a longer duration may encourage finer atomization and smaller droplets. As a result, a longer injection duration permits a longer spray penetration distance since the fuel is injected and driven forward for a further duration of time. And next is the result for effect of injection pressure and duration of volume fraction penetration. So the effect of injection pressure and duration are shown in that figure in the graph in the slide. And from the figure, we can see that the spray distance or length from the injector nozzle before it begins to disperse is influenced by injection pressure. Increasing injection pressure typically result in a narrower spray width. Higher pressure improve the atomization process and producing smaller and more concentrated droplet in the core of the spray cone. And this is the result for volume fraction penetration at pressure 50 bar. As we can see that from figure, actually this one we have simulate for 80 bar and 110 bar. So the result I want to discuss here for just for the 50 bar, and we can see that the wider spray penetration into an atmosphere is typically encouraged by higher injection pressure. The spray can travel farther before dispersing due to increased pressure, higher fuel velocity and momentum. The deeper penetration may present in larger fuel volume fraction in the surrounding air. The injection duration also affects the spray volume penetration. A longer injection duration enables a higher fuel volume fraction to be delivered, resulting in a greater fuel dispersion and distribution in surrounding environment. Remembering that there can be an ideal injection duration that achieves a balance between fuel dispersion and penetration that is crucial. It is also necessary to consider additional variables such as the fuel characteristic, injector design, spray angle, and environmental circumstances that may affect the volume penetration of the spray. So, as the result or as the conclusion for this project, I can say that the simulation flow on the fuel injection through the nozzle spray before the combustion process took place inside the combustion chamber is depicted in the study, and then the simulation was triggered using a single hole injector with 0.3 mm diameter. 3 distant injection pressure was set for the nozzle 50 bar, 80 bar and 110, and the injection pressure affect the diameter and length of the fuel penetration. The spray quickly evaporates and disperses as it gets larger, producing wider spray angle. This study revealed that the 0.3 mm orifice diameter had a broad spray cone angle. As a result, we can conclude that a rising ambient pressure causes the spray cone angle to rise. The fuel spray later spread existing the injector nozzle is called the spray width. As we can measure the variation in spray width by adjusting the injection pressure. Due to increased optimization and greater fuel velocities, a higher injection pressure frequently lead to narrower spray width. The coverage and distribution of the spray can be learned by measuring its width. Spray penetration is often increased by increasing injection pressure. And in conclusion, we can say that injector pressure impacted the spray penetration and width angle. From the result obtained, we can say that the spray width and length increase when the higher injection pressure is applied to a large orifice diameter. The higher injection pressure results in enhanced spray penetration, and the final atomization is produced because the fuel disintegrates more quickly under the higher pressure. So thank you very much for your attention, and hopefully you can get some idea from this research. And if you got any idea or any question to ask, maybe you can contact me through the organizer data for my contact. So thank you very much, and see you again next.